We're Group 6, and this is our Project 3. I'm Nick Wagman.
I'm Ned Landy.
I'm Cole Netzband. So we were asked to find the percent cold work of a steel cylinder, which we were going to make into a dagger. So we're assuming that the steel will stay as a cylinder throughout this cold work. So we want to get it from 5 centimeters down to 3 centimeters in diameter. We were also told that this dagger needs to have a percent ductility larger than 15% and a tensile strength larger than 800 megapascals. So we could start by taking the cross-sectional area and finding the percent cold work. So we do this by taking the original area, subtracting it by the final area that we want, this being the cross-sectional area, and then dividing it by that original area and multiplying it times 100 to get our percent. So since we're working with a cylinder, obviously it has a round end. So we need to take the area of a circle on that end. So what I do here is I take the areas and I substitute in the circular areas. And then we can take away the pi and the half out of all these because they'll just all cancel. So we'll end up with this equation here that takes the diameters and squares them and does the same thing as the normal area equation does. So when we do this, we take our original diameter of 5 centimeters, subtract it times our final diameter of 3 centimeters, and divide that whole thing by the 5 centimeters and multiply it times 100 to get our percent. Of course, these are all squared as well. I forgot to mention that. And that gave us a 64% cold work. So when we compare it to our graph for steel, we see that this line here represents the cold work, which it is. You just can't see it, but it's there. So the line for our cold work at 64% on both of these, it doesn't match up with the steel line at all. Like, it is completely off. And so in this situation, the steel is broken. Like, we've stretched it or cold worked it far enough to where it is just snapped. It's broken. It's done. So in that case, we're going to need to anneal it at some point. So like I said here, since we can't take it all the way from 5 centimeters to 3 centimeters without it breaking, we're going to need to stop somewhere between there to anneal the metal, to let it heal, and then we could draw it out the rest of the way to get our desired diameter and our desired tensile strength and ductility. So if we look at our graphs, we need a tensile strength greater than 800 megapascals. So again, hard to see, sorry. So what we see here is that the 800 megapascal mark is about the 13% cold work on this graph. And then on the percent ductility, we need it greater than 15%. So when we line it up again, we see that this is also about 13% cold work. So we can use this 13% as our new cold working value, and then we can solve for this new diameter that we will cold work to. So we'll cold work to this new diameter, we'll anneal it, and then we can cold work it the rest of the way to get our final diameter. So like I say here, we will go from our initial diameter of 5 centimeters, we'll take it to this new diameter, and that being we'll cold work it that whole way, we'll anneal it, and then we'll cold work it the rest of the way to the 3 centimeter mark. And so what I do is I take that last equation we used and I take out the initial diameter, and I substitute in this new variable, which would be this new diameter dn. So we want to find this dn, so I rearrange the equation into this one here, which will solve for the dn with respect to the percent cold work and the final diameter. So when I put in our numbers, we have 3 centimeters, and then we have the 13%, which we found by looking at the graphs. And we find that this new diameter is 3.22 centimeters. So again, what we will do is we will go from the 5 centimeter diameter. We're going to cold work it down to this 3.22 centimeter diameter. And then from there, we'll anneal it, and then we can finally go from this 3.22 centimeters down to our 3 centimeter diameter. And now I will hand it off to Ned.
So finding that 3.22 is going from 5 to 3.22. This is our intermittent stage. This is where the material can recrystallize and it'll form new grains. So once you form these new grains, the graph that we saw before just refreshes and you can start back off from how it was initially. So you're going from that 3.22 and then it's saying, okay, 13% cold work was done. That's giving us 800 megapascals and then a value of 15% ductility. So if we apply that same process to aluminum, so we're not actually finding the values for 800. Aluminum's not going to get to 800, as aluminum is much weaker than steel is. But if we take this same process and we take a 5 centimeter diameter rod of aluminum, there's 3 stages to that same work that we just did. So stage 1 is our initial cold work that we're doing. We're getting it from 5 to this 3.22 value, and that's going to be this first cold work that we're doing. So if you plug in the formulas that he was just using before, and then you can multiply it by 800, I think so you can see this is our 5, this is the 3.22, this is the intermittent, and it's 58.6% cold work done to get it from 5 to 3.22, which is where we want it. And then once it's here, we need to anneal and to heal. If we just tried to pull out the whole 64%, it would break, same as with steel. So then you go to stage 2 where you're annealing it. This allows it to get new grains, and then you could just start again for our stage 3 where you're going to be cold working using the same process as before. If you're going from 3.22 to 3, you're going to get the same value we found for 13.2. So this same process is just taking what we did with that steel, taking it from 5, bringing it to 3.22, and then bringing it back down to our desired value of 3. Now, if we take this 13% value we found, this is the graph for aluminum. So it's different than steel, so the values are going to be different. This is in KSI, so we just have to transfer that to megapascals in order to find out our work. But if you look at the graph for the percent cold work, if we take our 13% that we found for the cold work, and we just follow it up along the graph, we'll find that if we did the same process for steel, or for aluminum, sorry, that we did for steel, we'll only get around an 8% ductility compared to the 15% that we had within steel. And then if we take that 13 and keep following it up to the tensile strength, we'll only get around 151 megapascals. So this is a lot less than the 800 we needed for the steel, and then the 8% is also a lot less for the ductility we needed from the steel. So this just shows that the aluminum has a lot different properties than steel. If you try to do the same process, your dagger is going to be a lot weaker, and it won't do as well as the steel would.
So what we're looking at here is we're looking how the different samples changed when they were cold worked. So using our experiment that we did in lab, the unworked section of the aluminum had a hardness of 9.8. When we tested the cold work section, it was a hardness of 10.1. So this is showing that cold working does increase the hardness. And then same thing with steel. Unworked, it was at 44.3 hardness. And then when it's cold worked, it was 79.2. Again, this is just showing that it's going to be harder in that section where it's cold worked. So just comparing the two real quick. The steel showed a much larger change in hardness depending on where it was worked. So the difference in that hardness was, instead of roughly 1 with the aluminum, it was like 20 something. So that's just showing that cold working is making steel a lot harder than when you cold work aluminum. Because of this though, steel is going to be more brittle and less ductile, where the aluminum is more ductile and less brittle. So if you were to make a dagger with these materials, steel is going to be stronger and harder, but it's going to be more likely to crack. And then aluminum is going to be ductile and softer, but less likely to crack. So it'll be a little bit more flexible and a little bit less likely to break when you're using it. So this picture here, it's a little hard to see, but it's showing the different grain sizes. This is a sample of brass, but it's the same properties or same idea that you would get from the other materials. So the samples are becoming harder because of dislocation, entanglement. So all those dislocations happening in the material are entangling with each other and making it harder for the material to break. The samples will both show elongated grains, dislocation cells, and then there's also going to be strain bands like these here. So that's just showing that while this isn't the samples we used, that's what's happening when you cold work a material, and that's going to be what's making them stronger.